Okay, so this will be a little bit different. So when we're calculating the heat of reaction, delta H, it is for a particular reaction, a specific chemical equation. And it's for the molar amounts in that equation. So if we change the equation, then we're going to change delta X. If we multiply all the coefficients by 2, so there's twice as much stuff, we'll have twice as much energy going one way or the other, right? So if we take the chemical equation and multiply it by some factor, 2, 3, whatever, then you also multiply delta H by the same factor. So the example here, we've got this generic equation, A plus 2B goes to C, and this is delta H. By multiplying all the coefficients by 2, now I have twice as much stuff reacting, so we should have twice as much energy. And we do. So we multiply delta H by 2. Let's sink in for a second. Does it make sense that if you burn twice as much gasoline, you get twice as much heat out? Yeah? That's basically what we're saying here. If you burn 3 times as much, you'll get 3 times as much heat. Now you might wonder, well, why would we want to do that? We'll get to that later. If we reverse the chemical equation, then we change the sign on delta H. So here, going from A and B to C, we've got this value. If we run the reaction backwards, delta H has to have the opposite sign. If we burn the gasoline and it gives off energy, and then we found a way to unburn the gasoline, it would have to absorb that much energy, right? So the number's the same, but the sign is different. Because this is going forward, so it's that. Now this is going backwards, and so this will be negative. -1 times whatever that was. And then Hess's law says that if we can express a chemical equation as a sum of several different equations, then we can find delta H for that new equation by adding up the delta H's. So here we've got the one we were looking at, A plus 2B goes to C, and that's delta H1. And then here's a different reaction, C going to 2D, delta H2. If we add these two chemical equations together, we're making C, and then we're using up the C. And so that's not going to show up when we add those equations. This is like when we added the half reactions, right? Things that were exactly the same on both sides just disappeared. So adding this and this, I get this. And so the energy change here has to be equal to the sum of those energy changes. Now, what's kind of trippy about this is this does not have to be the way that the reaction occurred. It might have gone through some other mechanism. But if I can find two equations where delta H is known and I can combine them mathematically to get the equation I want, then I can calculate delta H. And that's because delta H is a state function. It doesn't depend on how you got there. It just depends on where you started and where you end up. So this is the book's attempt to try to show you this in a picture. So if we're starting here, and maybe this first reaction, the energy is going up, so it's that would be endothermic, energy coming in, so C is higher in energy. And then from C going to 2D, there's this big loss of energy. And so just like with elevation, so like if this is, let's just draw that in there. So if this is our mountain, And we're looking at the top compared to the base. And we talked about how you could take this long path up, or you could go straight up the side. Or what I said is I'd prefer to ride in a helicopter. So this would be like the helicopter, right? So you start here, you fly up there, you come over here, and you go back down. It doesn't matter how you got there, your change in elevation is the same. Whether you went from here to here, oops, stop that. Whether you just went from here straight to here, or you went up here and then back down. It doesn't matter how you went. There might be another one where you could go up here and then come down a little bit and go back up a little bit and come down. Doesn't matter. As long as we're just looking at the difference between beginning and ending. So because of this, we can determine a delta H for a reaction that would be really hard to directly measure in the lab. We can take reactions that have known delta H's, and there is so much information out there. That CRC book that we looked up the density of water in has pages and pages of delta H's for different chemical reactions. And of course, each of those represents someone doing that reaction multiple times and measuring very carefully, and probably someone in another lab also doing it. So much work. We can figure out how we can add those reactions together to get the products we want, and then we can do a similar calculation for the delta H's. So let's look at this one. So here we've got our original chemical equation, 2A plus B makes C, and delta H for this is 122 joules. The question is asking, what is delta H for this reaction? 2C going to 4A plus 2B. So what we need to do is think about, well, how is this chemical reaction different than that one? There's two ways it's different. It's going in the opposite direction, right? This was going from A and B to C. This is going from C back to A and B. So what do I do to the delta H then? I change the sign, right? So if we reverse, oh, that doesn't work. We reverse the direction. So now we've got negative 122. And what else happened? The coefficients have been multiplied by 2, right? So it was multiplied by 2, and so then we multiply this by 2. Whoops. Does that make sense? So here we weren't actually adding any equations together. We were just looking at what if we changed this one. We're running it in reverse with twice as much stuff. Well, then we're going to have twice as much energy change, and it's going to be in the opposite direction. It's like, buying is forward and selling is reverse, right? It's the same amount of money. But if I'm selling 2 pairs of shoes instead of 1 pair, then it's twice as much money, right? And if I'm buying them instead of selling them, or selling them instead of buying, the only difference is whether it's negative or positive, whether money is coming into my account or out of my account.
So question.
Mm-hmm.
What made you say that? Why did we choose the 2 and not like the 4?
Well, I'm looking at, that's a good question. Why multiply by 2 instead of 4? I'm looking at what the original coefficients were. So this was a 2, and now it's 4. This was 1, and now it's 2. This one 1, and now it's 2. So all the coefficients got multiplied by 2.
Oh, I see.
Yeah.
Gotcha. Okay.
Okay? Any other questions? Find delta H for this reaction. So here we have N2O plus NO2, make 3. No! That's yelling, isn't it? It's all caps. I think I woke somebody up. And we are given these 3 chemical equations with their delta H's, which, greatly simplifies this because we don't have to go looking through piles and piles of equations. We know that we're going to need all 3 of these and only these 3, and we can make this one come out. So there's different ways to approach this, but this is what I'm going to do. I'm going to highlight these because the N's and the O's with the 2's, they all start to look alike. So I'm going to make N2O be green. It's green highlight, and then there's one over here. That's the only place I see N2O. And then I'll make the next one, the NO2, I'm going to make that one red. And so I'm going to look through here. Oh, there's NO2. Highlight that one red. And it looks like that's the only one. And I'm going to make no be blue. So there's no here and no there. I think the puppy's beginning to think his name is No. So what I want to do is I can reverse these equations or leave them as they are. I can multiply them by 2, 3, 4, whatever I need, so that I can get them to add up to equal this one. So I'm just going to start at the beginning here, and I'm going to find an equation that has this green highlighted compound and make it be a reactant, because that's what it's supposed to be. Well, this one, right? Not to get the colors mixed up. So I'm just going to copy that one down. 2 N2O gas going to 2 N2 gas plus O2 gas. Now, have I done anything to that equation yet? No, I copied it. 163.2. So delta H will be the same. So let's highlight that one as green. But this has a coefficient of 2, and this has a coefficient of 1. We can take care of that as we go through, or we can fix it at the end. What do you want to do? The end, okay. So we'll just worry about that later. So I also need to find NO2 as a reactant. Well, the only equation that has NO2 in it is this one, but NO2 is a product. So I'm going to reverse the equation. So I'm going to write 2NO2 over here. And there's my arrow. It's helpful to line those arrows up. And then I'm going to have 2 NO and oxygen. And again, I'm going to highlight that so we can recognize what we're looking at a little easier. So as I write down delta H, I reversed the chemical equation. So what do I do to delta H? I reverse the sign. So up here, it was negative 113, negative 113.1 kilojoules. But I'm writing it backwards. So now it's positive. Let's see here. There's also a no in here that needs to be highlighted. Okay, so I have the green and the red one as reactants, and I have the blue one as product. That just kind of came along with the other one. But I've got these other things here as well. And I'm going to need those to go away. So I have one equation left, and that's this one. The blue compound is supposed to be a product, so I'm going to try writing this equation down here, and we'll see if that helps any. N2O gas plus O2 gas making to no gas. Did I change that chemical equation? No, I didn't. Ha, no. 182.6. So now we have to look at this and see, well, I've got nitrogen and oxygen on this side and nitrogen and oxygen on that side, but I don't have the right numbers of them. On this side I have 1 and 2, and on that side I have 2. So I could either divide by 2 or multiply by 2, one or the other. I'm going to multiply by 2 because then we can avoid having fractions, and most people don't really like fractions. So I'm going to multiply this bottom one by 2, and so that 2 becomes a 4. And then this gets multiplied by 2. So why did I do that? I did that so when I add these together, I have 2 nitrogens on the product side and 2 nitrogens on the reactant side. I have 2 oxygens and 2 oxygens. I can cancel out everybody that doesn't show up in the end equation. Okay? So now what we want to do is we want to add up our delta H's. Negative 163.2 plus 113.1 plus 182.6 times 2. So I'm getting delta H is 315.1 kilojoules. I'll just stick with the red. And so when I add this together, I get 2 N2O gas plus 2 NO2 gas is going to make, I've got 2 here and 4 there, that makes 6. 6? No. Oops. Is this equation the same as that one? Almost, right? How can we make it the same? Divide by 2, right? If I had fixed things as I went along, I would have had to do the math earlier. It's not really any shorter or better or anything. So I'm going to divide by 2. So dividing by 2, that becomes a 1, this becomes a 1, this becomes a 3, and I divide that by 2.
So we have to divide, why do we have to divide the delta H by 2?
Because we have to divide delta H, because if we have half as much stuff reacting, we're going to have half as much energy being transferred.
Okay, so whatever you basically do to the
Whatever you do to the equation, you have to do to delta H. Yep, exactly. And so our answer is going to end up being that delta H here is 157.6 kilojoules. Any questions? Let's try another one. Let's find delta H for this reaction. We've got hydrogen and ozone making water. And this time they only gave us 2 equations. We're supposed to use these reactions with these known delta H's. So I'm going to highlight again, I'm going to make hydrogen red, and I'm going to make water blue because that kind of makes sense. Water's blue, there's water, and maybe make ozone orange. Nope, that's not ozone. This is ozone. O2, O3, it makes a difference. So, trying to get this equation, I'm going to choose the one here with hydrogen in it and write it so that hydrogen is a reactant. So 2H2 gas plus O2 gas makes 2H2O gas. So they've got the blue one and the red one. And let's just do it the same way and leave the numbers till the end, the coefficients. So I did not change that chemical equation, so I'm not going to change delta H. Still minus 483.6 kilojoules. So I've got my red and my blue in the correct places. I need to get the orange in there, like the ozone. So this other equation has ozone, but it's a product, not a reactant. So I need to write it backwards. 2O3 is going to make 3O2. And so I wrote the equation backwards, so what do I do to delta H? I change the sign. Because the heat's going in the opposite direction. So that's negative now. So here's my ozone. I'm going to do this again to avoid fractions. I need these oxygens to cancel out. I have 1 oxygen on that side and 3 on this side. I could multiply by a third, but I don't want to do that. So I'm just going to multiply this one by 3. So I get the same number. It's a little bit like the half reactions. So I'm going to multiply by 3, so that's going to give me 6, and 3, and 6. And then I multiply this by 3. So I've got these guys are going to cancel out. So now, as I add these together, 3 oxygens and 3 oxygens, poof, those go away. So I'm going to write down what's left. I've got 6H2 plus 2O3. It's going to make 6H2O. getting kind of messy, sorry. And then delta H here, I've got negative 483.6 times 3 plus negative 285.4. Negative 1736.2 kilojoules. And I'm pretty close. But I need to get the coefficients the same. So I'm going to end up dividing by 2 again. So divide by 2, this becomes 3. Divide by 2, that becomes 1. Divide by 2, this becomes 3. And then I'm going to divide this by 2. So delta H is negative 868.1 kilojoules. You kind of have to be able to manipulate these things in your head, right? And turning this one backward, that changes the sign on this one. And 2 of these, well then I need double of this.